This is 9.5 part 2. How to solve x prime equals ax for a 2 by 2 matrix A. Step 1, solve determinant A minus Ri equals 0 for R. These are the eigenvalues. Those will give you the eigenvalues. Then for each eigenvalue, you're going to find an eigenvector by solving A minus Ri times K equals 0. Finally, the way you put it together is your general solution is what's in red here. C1K1 e to the R1t, C2K2 e to the R2t. So, in the previous example, this expression right here, 2, 3 would have been the K1. Let me erase all this. 2, 3 would have been the K1. And then the eigenvalue would have been 4, because this is K1 e to the 4t times C1. And then the negative 1, 1 would have been the big K2. And the eigenvalue would have been negative 1, because this is e to the negative 1 times t. So the vectors, the K1 and the K2, are here, the 2, 3 and the negative 1, 1. And then e to the R1t and e to the R2t are these expressions here. And then we put constants in front. And you can solve for the constants if you're given an initial value. Like we did here, you can solve for the constants, but otherwise, if you're not given an initial value problem, your general solution just looks like that. Okay, so let's do this with an example. Solve the system here. I'm not going to read it, but you can see it. And answer as both a vector equation and a system of two equations. So, first of all, let's determine what the matrix A is. If I write this in matrix form, this is x prime y prime equals 1, 2, 2, 1 times x, y. That's the matrix form of that system. So the matrix A is 1, 2, 2, 1. Okay, so the first thing I want to do is find the eigenvalues. So I want to solve determinant A minus Ri equals 0. Okay, so 0, I'm going to put the 0 on the left. 0 equals the determinant. I want A minus R times the identity. Now, what I'm going to do to get that is just subtract R off the main diagonal. So 1 minus R, 2, 2, 1 minus R. All right, that's 1 minus R quantity squared minus 4, which is R squared. I need to solve this, setting equal to 0, so I need to factor it. So before I can factor it, I have to unfactor it. R squared minus 2R plus 1 minus 4 is minus 3. And that's R minus 3, R plus 1. So I have two eigenvalues. They're negative 1 and 3. And I'm going to want to see that when you show me your work. I'm going to want to see that exact same thing. The equation you're solving, and then the determinant bars, factoring, and finding the eigenvalues. 2. We're going to find eigenvectors for each one of these eigenvalues. So that's going to be two separate calculations. Write down which eigenvalue you're working with. I need to see it. So for R equal negative 1, go up to step 2 here in the box. You want to solve A minus Ri times big K equals 0. So I want to solve A minus negative 1 times I. So A plus I times big K equals 0. Because it's minus a negative I. Okay, that's, now let's write that out as a matrix. So the matrix A plus I take the matrix A, which is up here, and I add on the identity. So I get 2, 2, 2, 2. K I want to write as a vector. k1, k2, and 0 I want to write as the 0 vector. Okay, so that's the system I want to solve. This gives me two equations. 2k1 plus 2k2 is 0. And the second equation, I'll write it down, but there's no reason to, because it's just a copy of the first equation. So we can just solve the first equation. 2k1 is 2k2, so k1 is negative k2. So I'll let k2 equal 1, and my solution is big K, and I'm going to call it big K1 because I'm going to have a K1 and a K2. Big K1 is little k1, little k2, but little k2 is 1, and little k1 is negative 1. So now I have an eigenvector-eigenvalue pair. This is my eigenvector, and it's paired with the eigenvalue r equal negative 1. So we'll put that together in our step 3 when we write down the general solution. Okay, now I'm going to do the same thing for r equal 3. I want to solve a minus 3i times big K equals 0. So a minus 3i, I look at a and I subtract 3 times the identity. Negative 2, 2, 2, negative 2. And I'll let big K be K1, K2, and that equals 0, 0. So that gives me negative 2K1 plus 2K2 is 0. And I'm not even going to write down the second equation, and here's why. The second equation is going to be 2K1 minus 2K2 is 0, but that's just negative 1 times the first equation. So the second equation isn't going to add anything. So I'll write it down. 2K1 minus 2K2 is 0, but I can cross it out because it's not adding any new information. So if I solve the first equation, I get K1 equals K2. So I'll let K2 equal 1. I pick K2 usually to be the smallest integer that will avoid fractions. And we have no fractions here, so I'll let big K2 equal little k2 is 1, and little k1 is also 1. And that gets paired with r equal 3. Okay, step 3, our general solution. Big X is C1, K1, which is negative 1, 1, e to the R1 times t, negative t, plus C2, K2, 1, 1, e to the R2t, and R2 is 3, so 3t. That's my general solution as a vector equation. If I want to write down the general solution as a system of equations, then I need to think of big X as little x, little y. Go on, go. And that gives me two equations. Little x is, read across the top, negative C1 e to the negative t plus C2 e to the 3t. Now read across the bottom, little y is C1 e to the negative t plus C2 e to the 3t. Okay, so now you guys give it a try, pause the video, do this one, and then meet me back here for the solution. And really, do it. Okay, I started part of the solution here. I wrote this system in matrix form so I could determine the matrix A, and then I started by finding the eigenvalues. I want determinant of A minus Ri equals 0, so I've got 0 on this side, Here's a minus ri. The straight bars mean determinant. I multiplied that out and factored. So now I see r is -1 and 4. Those are my eigenvalues. Now I need an eigenvector for each eigenvalue. So for r equal -1, and it doesn't matter which one you do first, I want to solve a minus -1, so a plus I times big K is 0. And so that's a plus I is 3, 3, 2, 2. K is K1, K2. And I set that equal to 0, 0. And that gives me 3K1 plus 3K2 is 0. 2K1 plus 2K2 is 0. I can ignore the second equation because it's a multiple of the first. So if I solve the first equation for K1, I get K1 is -K2. I'm going to let K2 equal 1. So my big K, which I'll call big K1, is 1 for K2, -1 for K1. And that corresponds to R equal -1. All right. Now, for R equal 4, I want to solve a minus 4i times big K equals 0. And that is, subtract 4i, we get -2, 3, 2, -3. K1, K2 equals 0, 0. So that's -2K1 plus 3K2 is 0, and 2K1 minus 3K2 is 0. Second equation is a multiple of the first. So if I solve the first equation for K1, I get positive 3/2 K2. All right, I don't want fractions, so this time, instead of letting K2 be 1, I'm going to let K2 equal 2. Then I won't have fractions. So my big K2 is K1, K2, K2, little K2 is 2, and then little K1 is 3. And that corresponds to R equal 4. All right, so my matrix, my vector solution is big X equal C1, K1, and if you're wondering where I'm getting this, I'm just reading it right off of, it's this red formula, C1, K1 e to the R1t plus C2, K2 e to the R2t. So C1, K1 is -1, 1. R1 is -1. And then C2, K2 is 3, 2. And then e to the 4t. So that's the vector form. And now if I want to write that as a system of two equations, I'll have a little x and a little y. Little x, I'm going to read across the top, -C1 e to the -t plus 3 C2 e to the 4t, and little y would be positive C1 e to the -t plus 2 C2 e to the 4t. Okay. For the third part of this set of lecture notes, I'm going to do a mixing problem with you.